Okay. Hi everyone. So the next talk is by Jatin Goel and it's about memory management in Python. So Jatin has around 5+ years of experience in various tools and automation, cloud services, REST APIs and everything. And he is also a member of Hyderabad Python group and he has a lot of interest with core Python and he'll be sharing a similar topic with you today. A few suggestions for attendees. So we will be taking a Q&A at the end of the session. And if you have any questions in the meantime, you can raise your hand using the raise hand option. Thank you. Jatin, over to you.
Thank you, Bharat. Thank you for the introduction. So, something that I'll just add to that set of introduction is currently I'm also working on products, ranging different kind of products, on-premise products, where we are working on implementing OAuth solutions from Google and Microsoft with those products. And mostly, like my passion is with core Python, so that's why memory management in Python. I'll quickly share my slides. Bharat, should I get started, or are we waiting for some more attendees to join? Okay, I'll just take 10 more seconds and then we'll get started.
Yeah, I was saying let's wait for 20 more seconds and we'll start.
Sure. Okay, folks, I'll get started. Thank you for joining in. And moving along, what is memory management? So first off, since this format definitely restricts the face-to-face interaction, I'm just going to assume that 70% of you must have faced memory limit exceeded kind of errors whenever you must have tried competitive programming on different platforms, let's say HackerEarth, HackerTest, or LeetCode. I'm just running a poll for this, so you can let me yes or no on the poll whether you have seen that memory limit exceeded error or not, and ever wondered why that happened. So this is what we'll be covering. Part of it is what we'll be covering in this talk. Knowing about so first question is what is memory management and why should you care? Knowing about memory management definitely helps you write efficient code. It also helps you to understand how and where you should do your object initializations so you can better optimize the memory of the Python program and also make sure that you don't over consume the resources, basically making it more efficient so that when it runs on a server with huge competition where it has to do huge cycles or like huge competition, it does not get stuck. Moving on, first let's talk about variables. I'll quickly rewind back to variables, C style variables, where we used to do the initialization like int a equals 5, which is like data type, variable name, and the value. Now, how it looks like in the memory in the manager is the variable, the location which is defined to that variable, and the value that is assigned to it, which is in binary. It is like we have defined that it is a fixed size and of the same data type. The variable a, if I cannot assign it, change it later to a character or a string. It will only be an integer. Now, if I later do a equals 15, it's still integer value, so value is updated. But what does that actually mean? So what it means is like the variable it just had the location. So a was having the location of the object where that value 5 was stored. When I said gave the command a equals 15, it went to that location, updated that binary value with the newer what the value that was provided. Now, how many types of variables are there in Python? You might be wondering four, five, so let's say string, integer, character, dictionary, list. So how many actually? And this would have been an interactive question, but you can let me know in the feed. Actually, the answer is there are no types of variables in Python. So Python, basically like everything, if you rewind back, everything is an object in Python. So what it means is Python has names. So every value, whatever you say, let's a equals 15 on a Python interpreter, it will just create an object in memory, which will assign its data type currently being set to integer and the value being set to 15. Now Python has names. So what it means is A is just a name that we have created which has a reference to the object which is storing the value 15. So if I go to terminal and do A equals 15, it will just create a name in the memory that this name, there is a name A which has a reference to the memory location where we have created an object which has the data type set to int and the value set to 15. How many types of objects are there in Python? There are basically two types. We have two categories of objects, simple and containers. Simple objects being numbers and strings, and where containers being dictionary list or any user-defined classes where we can store different kind of simple objects or container objects as well. Basically hybrid data types. How the objects are stored in Python is we have Python uses both stack and heaps. Stack is what uses to store all the variables and all the functions, and heap is where it stores the actual value or the data of that object. How does it so first thing is like references. We talked about names, we talked about objects, but what does actually the middle thing references mean? It's just that how many refer to that object. Let's say when we did a equals 15, how many names are referring to that object which has the value 15. So let's say this is the object 15, and this name A is just referring to that. So object is going to store a reference count, which is like I am being referenced by one name. So that is what we will be talking about next, reference count. So when I did, let's say on console, I went and did x equals 10, it creates an object 10 in the memory, and it creates a name x, and it binds a reference to that object. So this object has that counter, like how many object names are referring to that object. I'm saying names and references again and again. So let me know if there is any question you have in the session feed, and I'll take it up. I'll get to these questions later for books and others. Moving on, when we do y equals 10, so you might think like it will, what Python will do is create another object in memory which will have the same value 10 and set another name to it. Instead, it does not. So what it does is, let's say in C, if you do a equals 5 and b equals 5, it creates two different memory locations which will store that same value 5. But in Python, what it does is, once you have created the object x equals 10, it just created a single object. And then when you did y equals 10, it will not do something same as C, but what it will do is it will increase the reference count for the object 10. So now object 10 has two references to it, by name x and y. When you do z equals, so we already did x and y set to 10, but when we did went to z and created a list with those same value objects, same value set 10 comma 10, it just increases two more references to that same object. It again does not create any new object. Now references count, this is what we talked about, how we can increase the reference count to an object. Moving on, how do we decrease the reference count for an object? First thing is we can either change the reference count or change the reference itself. So earlier the name x was referring to the object 10. I changed x to a different reference, which is now a string abc. Basically it means it will create a new object in memory with the value abc, data type as string, and set x as the reference to that object now. Similarly for y, which is a boolean object in this case. Second way to decrease the reference count would be to use the delete keyword, del. So many of us must have used del x or like del some object name, reference name. So it will just delete that reference. Basically, it's not deleting that object. If you think that if you do del x, it will delete the object 10, it will not. So it will just delete the reference to that object 10. And it does not delete objects, it only removes the name as a reference to that object, just reducing the reference count by 1. Third way to decrease the reference count would be going out of scope. So when we do local variables, if we define a local variable inside a function, its reference count, so let's say in this example, inside a function test, I set x equals 10. And then that reference count for that object 10 is set to 1. After that, once I finish print and I exit out of that function, the reference count goes out of scope, so then the reference count is decreased. The object goes out of scope and the reference count is decreased by that number. So what happens when there are no references to an object? So in our first example, we had object 10 with two references x and y. If I change x equals abc, y equals false, so both references to this object with the value 10 are gone. Next thing, it is say it can now be safely removed from the memory. So this is just like moment of sin. I'll say local versus global namespace. So a lot of times, competitive programming also, sometimes what we do is create objects in the global namespace, and we tend to override that data. It just keeps on consuming that memory, and since it never goes out of scope, that memory is never collected back by the garbage collector. So it just keeps on increasing the memory of that program. That's why it's always recommended use local scopes namespaces as much as possible and restrict your objects in the global namespace. So as I was saying, global namespace, they never goes out of scope. Reference count never reaches zero because they are still there in the global namespace. There is no way that while the program is running, the reference count will never reach zero. It will only reach zero once the program has finished termination. So avoid putting larger complex objects in the global namespace. Moving on, this is how a Python object looks like in memory. In C Python, we have a PyObject class struct, and we set its type, the reference count, which is its value is 2, and then the value, which is 10. Uh, the Python object holds three things: the type, the reference count, and the value. Proof of concept, what we can do is, so let's say I have created an object x equals 10, y equals 10. When I do x equal y, I'm just doing equality check whether the values referenced by those two objects are same or not. So it will return me to true for both of those values. But when I do x is y, it checks like whether the memory address of both x and y matches or not. So I can, it also returns true. I can just test ID of X, which will return me the memory address of where, which memory that, the memory address of the object which X is referencing to. Similarly for Y, and I can see that both of those IDs match with each other. So two names, two references, but just one single object in memory. What this process is called interning. What Python interpreter does is at compile time, it will compile through your bytecode and see what are the static objects or compile time constants that it can intern at that time. So when it sees the first call x equals 10 in your program, it will intern that object. That first it will create an interning layer where it will intern that object, that any value with 10, I already have an object for it, and I already have a reference assigned to it. So moving on, point immutable objects, like it will only point to immutable objects. It will not work for mutable objects like list, dictionaries. So integer, string with the same value to the same memory location. So you don't need to do it by yourself. C Python does it by default as part of its memory optimization techniques. And we'll also cover how, if you want to intern your complex string yourself, and that is Python sys module, which has sys.intern, and you can give that object reference. So this is the example at play. If I do x equals height by and y equals height by, I can see the ID for both matches. The value equality check also is true, and memory address also matches for both. But if I do x equals height by bang and y equals height by bang, so it does not work. The reason is interning only applies to simple ASCII characters. It will not work on non-ASCII characters, which is like any special characters, caret, dollar, bang, at the rate, or any such special characters. It will only work for integer or string values. Moving on, so the pros of it is like it reduces the overall memory of the program. So you're basically creating a single object, even though it's referenced by multiple names at different locations. And if you still want to intern that object, we can do it like x equals sys.intern. And then when you do y equals sys.intern, it will do the equality check, and like the memory address will also match because it will just use that single object. But the cons of this is like CPU overhead. So you should only do it this manual interning only when you're using a lot of repetitive strings. And if you are doing, if you don't have too much repetitive strings, then I don't recommend that you use sys.intern module, intern method, because you'll end up consuming more memory. Moving on, garbage collection. It is actually a way for a program to automatically release memory. So let's say when garbage collector kicks in automatically in CPython when it reaches a threshold that will just get to in few minutes. So when the object is taking up the space and it has no references left, it can be released back to the operating system, that memory occupied by that object. So garbage collection, it checks for any free objects which don't have any references, and it will collect those and return that memory back to the program. There are two types of garbage collection, mostly reference counting and tracing. We just talked about reference counting. We add or remove references. The remove object is removed from memory as soon as the reference count reaches zero. So does that only remove that object? It does not. It actually does the cascading effect as well. So let's say you were referencing to x equals 10, and basically, what I'm trying to say is, if you are calling some object and you have a reference set to it, and you are using that object in some other data type as well, let's say dictionary, list, or class as well. So if that goes away, the upper class there, its reference count will also decrease. So that can also go away. So whichever objects are referring to them internally one by one, all of them will be taken away by the garbage collector. It's easy to implement and objects are automatically immediately deleted. But the bad is it has space overhead because we'll be storing the reference count for each object. And there is also an execution overhead because whenever we are accessing that object, there will be we'll be setting the reference count, increasing or decreasing that. And there is also this challenge that it does not detect cyclical references. So let's say I create a node class and I have node root, node left, node right. If I set this cyclical reference root, the reference count is 1. But I say do root dot child equals left. So reference count for left goes to 2 because it was already being referred to by this name left. And then when I do left dot child right, it increases the reference count of this. So right, the node right is being referenced by two things, right and right left dot child. But when I do left dot child equals left, so reference count for left goes to 3. The 3 being left being the name, then root dot child equals left, and right dot child equals left. So it is difficult for it to detect. Even if I delete those references, there is one cyclical reference between these which will still remain. That's where the tracing garbage collection comes in, which follows a two-way procedure, mark and sweep. So it will the garbage collector root will start a process. It will try to reach all the objects in the memory. So we talked about in the beginning that Python stores objects in stack and heaps. So stack has the names, but the actual objects are stored in the heap. So the mark and sweep algorithm, during the marking phase, it will start from the garbage collector root. It will go to the the heap of that Python program, mark all the objects that are reachable, and leave all the objects which are not reachable. In the next sweep phase, so we see that in this first phase, we marked all the objects that were reachable from the Python program. But then all these tail objects, they were not reachable. So garbage collector, during the second phase of sweeping, it will remove all those objects. So this will take care of our cyclical references. What does Python use? It actually uses reference counting as well as generational tracing garbage collection. So it is generational is basically a type of tracing garbage collection which is a little bit different. It is based on the theory that most objects die young. So we'll get to that. Actually maintains three lists of each object. So generation 0, generation 1, generation 2. Tracing, what it does is it will implement the tracing algorithm, the mark and sweep that we discussed, but at each generation now. So what it does is generation 0 will have the maximum limit of objects. Most of the times we'll just create temporary objects. So those will be stored in generation 0. Generation 1, so once let's say it has hit the threshold for generation 0, it will run the tracing algorithm, the mark and sweep, and then collect all the objects which have been removed. The objects that are left from that step will move on to generation 1. Let's say like these objects are still being used, and then when the threshold for generation 1 also hits, it will run the algorithm again. Then whichever objects remain will move on to generation 2, which will stay there for the lifetime of the Python program, because the assumption is it has already come through 3 cycles. That means these objects are still being used, and these objects will still be used throughout the Python program. So again, it does not store the simple objects. It only store the container objects whose reference count is still greater than 0. And when the Python number of project objects reaches the threshold, that's when the generational garbage collection algorithm kicks in. Now you might wonder how you can get the threshold for your Python program or update that. If you import the built-in module GC, you can do gc.getThreshold, which will return a tuple. The tuple is basically the number of objects that are there, the upper limit of number of objects in each generation. So value at index 0 is generation 0, then generation 1, so in generation 2. So you can have up to whenever the count of objects hits 700 at generation 0, it will run the tracing algorithm mark and sweep, collect all the objects, move them to generation 1. So all the temporary variables that we might have created will be removed at this stage. So how it works is it makes a list of objects to discard, runs the algorithm to detect the reference cycles, and then no outside references. It also adds them to the discard list. When the cycle is done, it will free up all the objects and repeat any steps for the younger generations. So what it means, like this last step is repeat all above steps for any younger generations. So let's say if the mark and sweep algorithm is running for generation 2, which is the highest, it will run the same algorithm for generation 1 as well as generation 0 to make sure that all objects are collected. After the cycle finishes, it promotes the surviving objects to the next generation, and objects in the last generation stays as the program executes. It will stay till the program terminates. And anyways, reference counting is still there. So as soon as the reference count reaches 0, object gets cleaned up immediately. And if there are any cyclic references, you need to wait for GC to run. So some of you might have still wondered if you have long running programs, and what happens is even though you are deleting those objects manually, let's say using the del keyword, or you are using local namespace and your objects goes out of scope, so hopefully that program should shrink in memory, right? But sometimes you might have seen that if you go to a task manager or activity monitor, you still see that the memory consumption of that Python program does not reduce. Have you ever wondered why? Meanwhile, I'll run this quick poll again to come back to the results. So what happens is fragmentation. Now we talked about that Python is using heap. So the program, first of all, the size does not shrink because the memory is not freed up from a continuous block. We have a Python heap which has the objects. So objects are stored at different locations in that heap, and it frees up that memory, but it's a fragmented block. It's not a continuous block. And then even if it's a continuous block, the Python program, the memory manager of Python, does not release that memory back to the OS, the system. It will just release that memory back to the Python program, so that Python program can use that memory for creating storing any new objects that are created. So memory freed up is released back to Python to use for any other objects, but not to the system. That's why we have to be careful, like when we assign objects, and especially be careful when we are creating objects in the global namespace. So now, by now, you understand how objects are stored in memory, how object reference count is stored, and how the thresholds are set, and how garbage collection is done by Python. But you might also wonder, like, how you can optimize your code, some quick optimizations that you can use in your day-to-day practice, so you can optimize, make your code more efficient. First thing is dictionaries versus tuples. So use dictionaries, try to use tuples as much as you can, because of course the memory consumption of an immutable object is very less compared to a mutable object. So tuples are immutable. Whatever values you have assigned to it, you cannot change it at any runtime. But for dictionaries, what it starts with is it will first create a dictionary in the memory with a lower limit. So let's say it will create a dictionary which can only store 2 objects. Dict A equals 1, B equals 2. So only two objects. As soon as you do a third object as a third object assignment to the dictionary, it will duplicate. So it sees that the limit has reached of its number of objects. It will create a new object in memory with double its size. It will not just create a memory object in memory with just one more size, but just double. So next time you do c equals 3, it will create a new dictionary inside the memory new object, which will have the upper limit of storing four objects. As soon as you hit 4 and try to assign a fifth object, it will double its size to 8, 16, 32. But tuples, they remain static, constant in size. And if you want to do a quick check, you can do sys.get size of. I'm doing it on an empty dictionary and empty tuple. So you can see the difference that 248 bytes are being used by dictionary empty, and tuple is just consuming 56 bytes. Similarly, for classes, what we have is like classes by default store all the objects variables in those classes as dictionaries. But with Python 3, we have a new dunder slots. So what dunder slots does is you can store the objects in that class as a tuple now. Uh, I'll see if I have some time towards the end to show you slots on terminal. So what happens, I'll just quickly continue over the presentation for now, and maybe we can also connect in the launch if you have any further questions on this. So slots, it is helpful when you're creating many instances of a class. Basically what it does is it will only allow you to update those variables that you have defined in the beginning when you created that class. But if you try to assign a new variable to that class, it will just give you an error, that attribute error, because attribute assignment cannot happen. So this is really helpful if you're going to create, let's say you have a base class and you are going to create thousands of objects of that class. It could be helpful in video streaming applications where you'll have video as a base class and you'll be having thousands of videos to play. And if you already know in advance that what properties the class should have, so that we do not extend that, like the size will not always increase. And since it's tuple, it will always have faster access, because dictionaries, it will, even though it does hashing, it will still take some time, but tuples, since they are immutable, it definitely gives you faster access. And you can do a further reading on this book for slots. I'll be sharing this presentation as well later. Second thing is weakref. So we talked about reference counting, and if you want to just create an object as a weak reference, so that let's say if the object is removed, what happens is you created x equals 10 and you did y equals 10. But if you delete x, that y object, the object with value 10 still remains in memory, because there is still one reference y added to it. But sometimes you just feel that I just want to have this reference so I can use that object, but I don't want to keep the object alive. The if let's say the actual reference x goes away. So weakref allows you to do that. You can just refer to that weakly. So if I delete x equals 10, I do delete x. It will delete that object 10. And if I already had y equals weakref 10, it will not keep that object alive. Again, I'll see if I can do the demo about this. So if you direct your attention towards the right side, it just adds a reference to an object, but which is not enough to keep it alive. When all the remaining references are only weak ref, the object will be garbage collected. Only the strong references, once they are there, it will not be garbage collected. But if I delete the strong reference, let's say x equals 10, I do delete x, that time y equals weak ref 10 it can still be deleted. And it is mostly implemented for caching and just mapping larger objects, mostly for caching only. So what did we learn? I'll just quickly summarize. We talked about Python. It does not have variables. It just have names, references, and objects. Then we talked about two types of garbage collection, that is reference counting and tracing. Tracing, what does Python use? That is generational garbage collection, which is a type of tracing garbage collection, but has three generations: generation 0, generation 1, generation 2. Now we know garbage collection is good because it helps you free up memory. So there is a freed up memory. When you create new objects in memory, it will just consume those the memory that was already freed up, but not request any fresh memory from the OS. We also talked about why does the Python program does not shrink in memory even though garbage collection is run. We quickly talked about slots and weakref. These are some of the sources that I've referred for preparing this talk. And additional readings. So this is a Python module of the week if you want to go to GC, and I recommend reading through this article how a company saved 9 GB of RAM with just using slots. They did not do any other modification, just move from using slots for creating their class instances. Then the vgraph and a blog on Python memory management. Okay, I'll be taking questions now. I think we are already out of time. So Sanchit has a question like how can we decrease the memory usage of a Python application? So it's already consuming 5 gigs and he wants to bring it down to 3 gigs. Again, it depends on how much you can optimize it. So we talked about we can use local namespace as much as we can. So that will just take away all the objects as soon as they are removed. The local name as soon as they go out of scope, the reference count will decrease, and those objects will be collected by the garbage collector. So that freed up memory is there with the Python program. And anytime a new object is being created by the Python program, it will not request additional memory from the system. So that limits how much memory we are consuming from the OS. Next thing is we talked about slots, which can be used for creating user-defined classes instead of the dictionaries that are used by default for classes. So that way, I'm just limiting the. We already talked the dictionary. Sorry, tuple consumes less memory than a dictionary. So slots internally uses tuple. So it is basically consuming lesser memory, which gives you faster access. So your Python program gets faster, and let me just so your Python program gets faster in execution as well, and you're basically end up consuming lesser memory. So I already have a link for a blog in my slide, which talks about how the company saved 9 GB of RAM. Hope that answers it. Yes, so Bhaskar asks, can we change the threshold of the number of objects in generation? Yes, we can change that. The GC module allows you to set the threshold of each generation as well. We saw that gc.getThreshold just returns us the threshold of all three generations in a tuple. Similarly, using gc.setThreshold, I think we can talk that about in the launch. So that allows us to increase that threshold. We can take a heap dump of all the objects, or the sys module allows you to detect like how the object is being created and how the memory is being assigned to that object, and you can also see how interning is happening using that sys module, and how basically that object is being assigned created in memory and assigned to that memory. And you can also, I always recommend using profiling when running your Python applications, so you can understand which method or which variable is being called how many times, and how much is the time taken by that method or that variable assignment, and how much is the memory being consumed. So profiling, there are some really good profilers in the Python world. So you can use the built-in C profile as well, or I tend to use Spider as my IDE, and it has a built-in profiler, and I run that profiler, which gives me a good dump of how much memory and CPU time it is taking. Moving on. So deep copy and shallow copy. Parag asked like in deep copy and shallow copy, how memory get handled in that. So deep copy, when we are doing, it's basically creating new objects in memory. So it is in deep copy, if you have nested dictionaries or nested lists, it will create a deep copy or like duplicate those objects in memory and assign new references to it. But in shallow copy, it will just create a new object for the root object, but create a reference to the existing object for the nested ones. So that saves us some memory in shallow copy. But if you, since it's still pointing to the same object in memory, if you overwrite any nested list with something, that change will be reflected in the original one as well. I'm checking the feed. Bharat, do you have any questions that I might have missed?
Yeah, there's one question which is any good reference for memory management while using Pandas library?
So that's one thing. I don't work continuously work with data science and pandas libraries. So I work mostly on core Python. So I cannot help you with that, but definitely we can look it up. We can connect over the lounge, and we can definitely look it up together. Right. I think we are already 5 minutes above our time.
Yeah.
I can definitely take any questions in the lounge area, so I'll definitely directly head over to lounge and take the first table that is available.
Yeah. Everyone, please connect with Jatin in the lounge area. We'll be having a lunch break and we'll be ending this session now. So please connect back for other sessions. Thank you.
Thank you, Bharat. Thank you, everyone, for joining. Great day. Bye.